Hello everyone, this is Professor Kuehn, and today I want to talk about Chapter 22 of A Student's Guide to the Great Physics texts. This, like the other ones, was about Book 1 of Newton's Principia, that's the reference. We have just finished Chapter 21, where Newton introduced his axioms, or what are now known as his laws of motion. And so what I want to do today is talk about Chapter 22, which is entitled The Conservation of Momentum. We probably will not get all the way to the topic of conservation of momentum today, or at least in this lecture, but I'm building up to a position where we can talk about conservation of momentum. So here's a basic question that is being asked, is what are some of the implications of accepting Newton's laws of motion? Or what are the applications, you might say, of Newton's axioms or laws of motion? And the answer is that we can use Newton's axioms to deduce all of the forces that are acting on a body when it is at rest. That's the subject of statics. And we can also use Newton's axioms to deduce all of the forces acting on a body when it is in motion. That's the study of dynamics. And to do this, we must be able to do two things. So this is sort of some background here. We must be able to, first of all, we must be able to add or compose forces. This is how Newton begins this chapter, is talking about how to add or compose forces. And secondly, we must be able to decompose forces, that is, into their components. And that's components. Okay, and that is what Newton talks about in his Corollary 1. So maybe I'll just say one thing about this. So in the previous chapter, Newton had his axioms, and just like in a mathematics text, there are going to be certain corollaries or things that follow from his axioms. Okay, so his Corollary 1, he talks about how to compose or add forces and how to decompose forces. So he draws a diagram that looks something like this, and he says, let's suppose that you have a force that is being applied to some body, and the strength of that force is proportional to the length of that line segment AB. You know, that could be like a 10 Newton force or a 30-pound force or whatever you want. So let's suppose there's a force that's being applied in the rightward direction with a strength that's indicated by the length of that arrow. And if you were to apply that force, that would cause the object to accelerate to the right. But let's suppose at the same time that there's that force being applied, there's another force that's being applied in a different direction. This would be force AC. So that is a force that, left to itself, if you got rid of this force, if you were just to apply that force to the body, it would make the object accelerate in kind of that downward diagonal direction. And so the question that Newton asks is, what happens if both of these forces are acting simultaneously on this object? And he says, well, you can just sum the results of these, but there's a special way to sum the results of these. He says a trick for summing these is to construct a parallelogram like this. Remember, a parallelogram has two pairs of parallel sides. And then to draw another arrow that goes from the dot right here across the diagonal, and we'll call this force AD. And the point he's trying to make is that if you have two forces acting on an object, force AB and force AC, it's the same result as if it had a single force AD acting on it. So forces AB and AC give the same result, and by that I mean the same motion, as if a single force AD was acting on the body. Okay, so this is giving us a way how to add forces. Okay, and then, so that's the first thing we want to talk about, how to add these forces. And then it's also going to be helpful to learn how to decompose a force. So for example, let's suppose we had a single force acting on an object, and we denote that force by this arrow like this. So the direction indicates the direction that the object would accelerate due to this force, and the length of that arrow represents the strength of that force. Well, it's oftentimes going to be useful to decompose that into a sum of two forces. So for example, if we set up a coordinate system like this, where this was like the x-axis right here, and this was the y-axis right here, this force acting on the object does the same thing as if there was a force, we'll call this force F. And we'll call this force F sub x because it's the force acting directly in the x direction. So if I sort of drop a perpendicular here, and then I drop another perpendicular over to here, Whoops, that's not very straight, but there you have it. Now let me go back. So if I were to have a force over here, right, and I'll call this Fy. So in other words, this force acting on the object would have the same result as if these two forces, Fx and Fy, were both acting on the object. So you're decomposing this force into a sum of two other forces. Notice that there is not a unique way to do this. I could take that exact same force, F, and if I drew a coordinate system, so here is, I could draw my coordinate system in some direction like this, the x and y axis like this and this, right? And then I could project that force here, and this would be the force in the x direction, F sub x, and this would be the force F sub y. So it's the exact same force, but because I am drawing coordinate systems in a slightly different direction, they're going to be two different forces that add up to this force. And there are literally an infinite number of ways that you can decompose a force into two other forces. And the particular decomposition that we use is going to be dependent on the kind of problem we are trying to solve. Okay, so that is the first thing that Newton talks about in this chapter. This is his Corollary 1, how to add forces and how to decompose forces. We'll come back to this later when we're solving problems. Okay, let me say something else here. This is about his Corollary 2. I'm not going to spend a lot of time on this, although he does. And the point of this, which is sometimes called Newton's wheel. Newton's wheel. The point of this is that we can figure out all of the forces that are acting on something in a very complicated situation. So he talks about, let's suppose we have an axle right here. And he doesn't draw these lines, but I'm going to draw them. So you imagine that this is, let me pause here for a second. So this is one of the axles of the wheel. So you might imagine a wheel like this. And this is a spoke on the wheel. And I'll call this point right here O. And on the end of this spoke at this point, we have a string hanging with a mass P, like that. And so if this wheel had this single spoke and a mass hanging, of course it would try to make this wheel rotate around in the clockwise direction. But he's got another mass hanging on. He's got another spoke here, and he's got another another mass hanging over here, mass A, and he labels these points K and N. And he says, well, if you have a situation like this, one can figure out how much, if you know the distances from O to N, and also from O to K, one could figure out how much weight you have to hang from these in order for this wheel not to rotate at all. So the axle, he says, will be in equilibrium, or it will not rotate, if the torques, he doesn't use that term, the moments, if the torques or moments acting so as to rotate it clockwise and the torques acting so as to rotate it counterclockwise balance each other. How would you do this? Well, this one you can see is trying to make it rotate in the clockwise direction. This one is trying to make it rotate in the counterclockwise direction. If you decompose this force right here into a part that is tangent to the rotation direction, tangent to the wheel, and one that is in this direction, then this weight, we can maybe call this force right here the weight. The weight like this, maybe I'll call this the weight that is, I don't know, tangent, and I'll call this the weight perpendicular. The tangent component of the weight is the part of the weight that is trying to rotate the wheel. The perpendicular component is not actually trying to rotate the wheel at all. So this is an example of how to decompose this weight into two components, one of which is trying to rotate it. Okay, so this one right here is trying to rotate it clockwise. This one, which is already tangent, it's already at a 90-degree angle, is already the entire weight A is trying to make it rotate in a counterclockwise direction. So Newton kind of goes through this problem as an example of how to decompose forces. In fact, he makes it even more complicated because this weight isn't hanging straight down. It's sort of, he imagines taking a board or some kind of ramp right here and pushing it against this weight, so this string is hanging at a funny angle. So it makes it even more complicated. So this is basically trying to show off how complicated of a problem you can solve using this composition and decomposition of forces. I don't want to spend a lot of time on this, so I won't. I'd like to go on to Corollary 3, and so I think I'll pause here and take that up in the next lecture.